Hey everyone, Professor Dustin here. This is going to be a review problem on standing waves. This is going to be like section '06. We also did this during exam 1 review, number 5, and then the first exam, number 3. So a problem like this might go, you have a half open pipe of length 75 centimeters. What is the wavelength of the lowest 3 standing wave modes in the pipe? If the speed of sound in air is 340 meters per second, what are the frequencies of these modes? So this might be like a part A would be what is the wavelength of the lowest 3 standing wave modes, and then if the speed of sound in air is 340, what are the frequencies of these modes? So the important thing to remember here is that, when you create, so I'm going to draw a half open pipe like that. You have to remember the conditions that the standing waves can have in a pipe versus a string. So if you have a string has 2 fixed ends, right? So that means that the 2 ends cannot move. So if I'm going to start drawing waves the string can vibrate while the ends are remaining fixed, it can vibrate like that. It can vibrate like that. It can vibrate, the next one getting hard to draw, like that, where the ends are remaining fixed. The ends are not, allowed to move up and down. This is the lowest 1, 2, 3 mode. For the pipe, the lowest mode does not look like the lowest mode for the string because the pipe has an open condition on this end. It's a closed condition here, so this end cannot move. This end is going to look like one of those. But this end is open, so it's the opposite of this. It has to be allowed to move. Remember the ways that we drew that were like, and I'm just going to draw a random one. We drew that like this. So this is the wavelength, this is the motion of the air, and then you just have to be careful and sort of like end it that way. So that's not the lowest, that's just 1, but that's the condition we have to satisfy. Fixed at this end, meaning it has to be in the middle. Open on this end, meaning it has to be down there. And remember, I also sometimes drew them like this, because that's actually what's happening, right? Is that the waves are bouncing back and forth, so they're like instantaneously here, then instantaneously there, and actually everywhere in between. So I have a video on that if you want to check it out on our Canvas page. Anyway, so this is what I want to do, is I want to draw these for the lowest 3 standing wave modes, find out the wavelength, and then find the frequencies of those modes too. So let's do that. So there's my pipe. It's got a length of 75. The lowest mode, the very first one, is the very first time that I can draw a fixed point here and an open point there and there. So clearly what that is just like this. And if I want to draw the opposite side, it's like that, right? And let me draw the other ones, the next 2 as well, just so we have them in front of us. So the next one is, the next time I can make an open end is I have to go through the first open end and then get to the next one like that. Right, so the first open end was like here, but then like if I try to add more and more of the wave into the pipe, I can't even fit it unless I put this one right here, which is the next time it's fully open. If you think of the wave, I guess this is a little silly, but I'll draw this. So if you think of the wave as doing this, and I'll draw the other side of the wave too. So this is like the snapshot as the wave goes up and down. That's one end of the pipe, no problem. When's the first time I get to an open end? It's right there, right? That's what this one looks like. If I try to fit more and more of the wave into the pipe, I got to get there until I can fit it, and that's the next one. So you can see what the next one's going to be from here. If I keep going, I can't make the boundary conditions work until I get to this one. So this is the next one, and this is where they get kind of hard to draw, because I need to draw like 2 bumps. 1, okay, that's terrible. 1, 2, 3. Okay, so I think that's right. Yeah, so you can see open there is the first one, there's the second one, there's the third one. Okay, cool. So the first challenge is to, now that we've got the good drawings, is to figure out the wavelength of these modes. Well, what's nice is we know the length of the pipe. So all we have to do is see what fraction of the wavelength is inside the pipe. So let's go back over to this picture and notice that that is 1 wavelength. That's 1 lambda, right? If I start here and I go up, then down, back to the middle, down and back to the middle, that is 1 entire cycle. So that's 1 wavelength. So go over here and compare how much of this of a wavelength is this pipe, and you can see that it's only 1/4 of a wavelength, right? We've only got that much of the wave in the pipe. So then I can make a little sort of a silly little equation, call that L, meaning that only 1/4 of the wavelength is L. So just to check to see if that makes sense, the wavelength, 1/4 of the wavelength is equal to L. Yeah, that's the formula, right? So then the wavelength, and I'll call this like 1. I might call it 0 for the lowest, but who knows, 4L. So it's pretty easy. 75 times 4 is 300. So the lowest centimeters, the lowest wavelength mode is 300 centimeters. So now that was this one. So now doing this one, how much of the wavelength is fit into the pipe? It's not even a full wavelength yet, right? It's still some fraction of a wavelength. We'll go back up here, and you can see that that is the division. That part of the wave is what is fit into the pipe. That's 3/4 of a wavelength. So that means it's 3/4 wavelength, lambda 2, let's say, L. So lambda 2 is 4/3 times L. 1/3 is 25, so this is 100 centimeters. Guess we should check that. Okay, checking that was a little silly, but indeed 100 centimeters is the right answer. The last one here, I mean, you can probably figure out the pattern. The pattern looks like it's going to be 1, 3, 5/4, but like, let's be a little careful about that. So we're going to go all the way over here to there. One wavelength is right there, and you can see that, yeah, so that's one wavelength. We've got another 1/4 of a wave. So yeah, 5/4 lambda 3 equals L, and that means that lambda 3 is 4/5 L. 1/5 of 75 is 15. So 15 times 4 is 60. And I guess I will stupidly check that in my calculator as well. Yes, indeed, also true. So those are the lowest three modes. So notice when we said lowest, what we meant was the longest wavelength, the second longest wavelength, and the third longest wavelength, and they're getting closer together, right? This one was a full third of that one, but this is only 60% of that one, so they're going to get closer together. You can memorize these formula. In fact, you can put them on your sheet, I guess, if you want, right? But to me, it's much better to sort of know where they come from, because what if you transcribe them wrong on your sheet? What if you make a typo or something, right? It's better to understand where they came from and then maybe use your sheet as a reminder or something. Anyway, so lowest 3 wavelengths. Next, what do we have to do? We have to figure out if the speed of sound is 340 meters per second, what are the frequencies of these things? So remember the basic formula, the velocity of the wave is lambda times f. We often do this when we do electromagnetic waves. We use the velocity c, but here we're using the speed of sound, which we're told the speed of sound is 340 meters per second in air. So this is very simple. If we want to find the frequency, we're just going to do the velocity divided by the wavelength. So all three of them look like that. The sort of key physics understanding thing here is that the speed of the wave is unique to that wave in that medium. So all of these waves, although the wavelength is changing, they have the same speed, 340 meters per second. So while the wavelength might be changing and the frequency is changing, the speed is the same. And so this is the pattern you get, just the wavelength, the speed of the wave divided by the wavelength for each case. And there are your answers. So just be a little careful that we calculated the wavelength to be, for instance, for the first one to be 300 centimeters. But of course, this velocity is meters per second. So really when I calculated the first frequency, I did 340 divided by 3 meters. That's how you get the consistent units. The answer is 113, and the units cancel. You get 1 over seconds for the units. That's hertz. So just be careful about the conversion here. It was natural to give you the pipe in terms of centimeters, but the speed of light, so the speed of the wave is meters per second. So the units have to be consistent. And notice that this is where the language lowest mode comes from, is that the lowest frequency is the lowest mode, corresponds to the lowest mode. It did correspond to the largest wavelength, so be a little careful about that. Unfortunately, it's not too hard. I mean, it's not too easy to get confused because like the opposite, the high frequencies, meaning if you go up here and you go down in lambda, those are the ones that are like impossible to draw because you can get infinitely high, you can go infinitely high number of, like, that's not even enough. That's like the 7th or something, right? So you're not really going to get confused about what the low and the highest are. Just want to note that the language lowest mode comes from the frequencies being lowest. And finally, notice there is a pattern here. The second one is actually 3 times 113. The third one is actually 5 times 113. So all the higher frequencies are multiple of the original, which is called the fundamental. So that's a good way of checking your answer. But notice that it's 3, 5, 7, 9, and so on. For the half open pipe, you get this setup of integers 1, 3, 5, 7. For the string and the closed pipe, you get multiples of single integers. So you get like 1 times 2, 3, 4, 5. You get all of them. But for these guys, you have missing harmonics. That's one reason why some instruments sound different, is instruments which are based on open pipes are missing every other harmonic, and so they have a different timbre. Anyway, that's beside the point. Here's the answer to this question. All of these problems kind of look like this. They could be a doubled closed pipe, half open, or a closed string, and those are pretty much the only possibilities, and they all kind of go like this. Find the lowest frequencies, highest wavelengths, and then using the speed, find the other one, or maybe if you have the wavelength and the frequencies, find the speed, whatever, stuff like that. Okay, I think that's it for this problem. Thanks. I'll post it and get to another one pretty soon.